So for this training video, we will discuss about finding the drag coefficients using Solidworks flow simulation. So this is a beginner's lecture for conducting CFD simulation using Solidworks flow. So in order for you to have an idea on how to perform CFD simulation using Solidworks, so first is we will use this model. So for our initial simulation, we will model a sphere with a diameter of 50 mm and using a revolve base using 25 as the radius. So because we will need to prove that our CFD uh, is based on the working formulas that has been proven by Reynolds. So we will use the Reynolds number, which is equal to the inertia forces over the viscous forces, which is equal to the density times the velocity times the diameter of the pipe over the viscosity. Then we will correlate this value in finding the drag coefficient, wherein the drag coefficient is equal to the drag force over the area times the density times the velocity squared over 2. So wherein we will have the value of drag coefficient. So drag coefficient is very important in computing in assessing if your design is aerodynamic. It will affect the lift and drag of your design. So basically, we have the standard shapes that we are using: the flat plate, prism, bullet, spear, and the airfoil. So as you can see, the airfoil is the most aerodynamic shape or object because of having a drag coefficient of 0.045, while the flat plate and the prism are over the 1 drag coefficient value. It's about 1.28 and 1.14 for the prism. You could see that the bullet is also aerodynamic of about 0.295, and for the spear we are expecting about a value of 0.07 to 0.5, which is particularly to the affecting the velocity that we are using and the Reynolds number. So as you can see, this is the flow, wherein this is the considered as the drag force that will affect the drag coefficient value. Okay, so meaning if we have higher drag force, meaning we will have to anticipate greater value of drag coefficient, which is we don't like if you're looking for an aerodynamic design. Okay, so we will be anticipating this one. So we will be inputting the velocity initially at the Reynolds number of 10. This is the standard viscosity, and we have the standard density of the fluid and the diameter. We will do the mathematical computation. We will have this velocity results to 0.003 meters per second on Reynolds number of 10. Then we will correlate this value to this graph. So what is the drag coefficient? If we plot this at Reynolds number of 10, will it be 4? So we will need to know during our simulation. Okay, to start, we need to model a sphere with a diameter of 50 mm. So I have already this model. So to model this one, you need to draw a circle, then cut it, trim it, and input R25 to model it, this one. Okay, once you're done, you need to go to the activate the Solidworks flow simulation. For this example, the Solidworks is model 2013. So you need to go to the add-ins. So go to the add-ins using the options, add-ins. So it will take a while to load for this one. So if your Solidworks flow simulation is not yet active, you could select this one, flow simulation. Or you could also right click this one and you could select flow simulation. Alright, so once you have this one, you need to go to your wizard. So this figure will be displayed. Okay, so we have to select wizard. So this is the start of doing a CFD simulation using Solidworks. So we have to indicate the project name. So Sphere CFD. Okay. So if you have to, this is the preview of what you need or what you are expecting to set up for your input data. And these are the results. So after that, go to the next. So we need to indicate the SI, the unit system as SI. So this one is already set at SI. You could see that it's already, the units are already formatted on SI units in pascals, meters per second, kilogram, meter. But you have an option to select IPS, which is inch per second, and feet, and CGS. So go to SI again. Next. So for this one, what you need to do is select external as the analysis type. Since we are simulating cylinder as sphere, so we need to select external since we are simulating the outer body of the sphere. But if you are simulating an inner part, you have to select this internal analysis type. Okay, so select external. And if you don't consider cavities and internal space, you have to uncheck this one. So we have this physical features, so we will explore it on the next training. Next is we have to select our fluid, which is the gas. Under we have to select the air. So gas and air, and select add. Okay. Then if you don't consider this one, just need it to leave it unchecked. So if you need to add more fluid, then you could add, and you have an option to remove. Okay, next, and you need to consider heat transfer. So we have to replace the adiabatic wall. So but if you are not considering heat transfer, just leave it. So if we need to consider it, just select this one on the drop down menu. Next, so under initial conditions, we have to set the velocity to 2.003 meters per second. So to simulate Reynolds number of 10. Okay. So to go to the x direction, so 2.003. So these are the defaults parameters, thermodynamic parameters and velocity parameters. So yx, so you have to consider that the direction is pointing to the x direction, this one. So because we want to set up our simulation in this direction, so that's why we put the x. But if you want to set up the flow reverse, you need to input negative. Okay, once done, you will have your flow simulation. Okay, so you have this setup, your input data and your results. Okay, for the computational domain, it is where your simulation will be focused on. Okay, so this is a box. You can select 3D and 2D. So, but you can select 2D if you are saving computational time. But if you're not, you need a better simulation, you need to activate 3D. Since if you're also considering multiple parts, you need to select 3D. Okay. Fluid subdomains and boundary conditions will be tackled on our next training video. So moving forward, we need to adjust the mesh resolution. By the way, mesh resolution signifies about the accuracy of your simulation. So the default is 3, but we could alter it to 4 as stated to be more accurate, but we could select it to 7, but it will incur more time of solving it. Okay, then once done, you need to add the goal. So Solidworks has the power of getting the values for you. So for this one, we need to find the GG force in X direction to solve for the drag coefficient. So we select GG force in X. So as you can notice that this have value of minimum, average, and max. Okay, so as you can see, there's many parameters in here: density, mass. So the Solidworks could already provide it to you. Okay, then after setting up the GG force in X, we need to set up the equation goal to find the drag coefficient. So as you can see, drag coefficient is computed by using the formula of drag force equal to 1/2 times the density times the velocity squared times the drag coefficient times the area. Okay, so we set up it in right click, insert, equation goal. So you have to select no units, so that's already correct. So you have to input GG force times, since we are looking for the drag coefficient, we will already multiply it by 2 because 1/2 over, open close parenthesis, since we have multiple parameters we have to include. So first is the density 0.204 times the velocity, which is 0.003 squared, times the pi, which is 3.14159, times r squared, which is 0.0025 squared. Sorry. Okay, so we will need to remove it, change to no units, since this one is set up for the drag coefficient. So just select it, 14159, and we're done. Actually, you could rename it. Just click this one. So it's a CD. Okay, for you to remember your setup. Okay, once done, we will go to run the simulation. So before you do the simulation, you have to save your setup first. So we could do this option, run, or right click on the sphere CFD and run. You can choose either of the two. By the way, I forgot, if you want to alter your setup, you could right click on input data and go back again to your setup fluids. Okay, now we will run the setup. So we run. So initially the solver will be prompted after we choose to run. So initially, if we don't have initial settings, we need to mesh the model and solve for a new calculation. Then select run. Okay, once done, the solver will be prompted. Okay, this one. So this solver will be prompted. So actually we could select preview, this one, view. Okay, insert, view. So we can select this one. So can select insert preview while doing the model, while Solidworks is doing the calculation. Okay, okay, so the solver is already finished after 89 iterations, and we could see that the solving has finished by 4 minutes, so we need to close this one. Okay, so upon moving the simulation, so we have gathered the same iterations. So we will go to the result plot, insert cut plot, and check for the velocity value. So input the stated here, so velocity and x and 255. Okay, so let's go to the results. You can see it already has the file name 2.fld. So right click on cut plot and insert. Select the front plane where you will plot your results. So we have display options. For the simulation, you need to do contour. So I have to select velocity in x. So we need to now change the number of levels, because the more number of levels, we will have a detailed value here. And check. Alright, you can see this is the cut plot of your simulation. So you can see the color pertains to the value of up to the negative 1.56, wherein you have negative velocity or opposing velocity or a backflow, and signifies your velocity overall at 0.003 meters per second across this area. Alright, so to make your model or your cut plot better, you need to deselect the flashlight, this one. Okay. You make a model more your cut plot better for viewing. Okay, you'll also do animation here for your cut plots, but it will be better if using your flow trajectory. So next, we need to check our value as a goal plot. What would be our value, but so we need to hide it first, hide all. But to make it more better for your viewing, we'll consider insert flow trajectory, then select a plane where the flow trajectory will be reference of front plane again. Our reference will be, the flow will be represented using different types of directional flows indicators. So we'll use sphere, so we consider velocity and x. So how many? So first I will do 100. So making it more number of points or levels will make your simulation slower. Okay, so flow trajectory is used to signify where is the fluid coming from the input to the output. You can see by using the animation flow. Alright, so maybe the factor that I'm using sphere is a bit corny, so we'll use lines with arrows first. This one is better. So if you just play it, see where is your simulation coming from. See that? So you need the 0.00t, and upon passing through this one, it slows down. So that's what happened in your simulation. So show again your simulation and your cut plot, and you have this beautiful, colorful picture. Okay, actually you could select different pressure parameters. So pressure. So since we don't consider the change in pressure, we don't have this parameter. So we expect the same color density also, nothing changed. So go back to here. Okay, let's go to the goal plot as stated. So right click on goal plot and you select either DG force or CD or all, and show to have the value. Okay, as you can see, we got the value of drag force of 4.41 times 10 to the negative 8 Newton, and we have the drag coefficient of 4.15. So 4.15, remember. Okay, so if we will use this graph, Reynolds number of 10, you can see. So we use this chart, Reynolds number of 10, intersect in this one for a sphere. You could see that what? You will almost get a value of 4 to be exact. Alright, so means that our simulation correlates to the Reynolds number 4.11. For my simulation is 4.15. So we get the value or the average value. So means that they're almost the same as results as compared to year 2013. So 4.15, and mathematically we are correct. It correlates. So that's why CFDs is using Solidworks is dependable. Right. Okay, then for this one, we will clone the study at Reynolds number of 10,000. What will be the result? So using SolidWorks simulation, save your file first, then clone it, then just RE 10,000. So what would be the result if you change this one? So notice that we clone this one, so we need to go to the input data, settings, so then initial condition, so 10,000, so it will become 3, apply, okay, then go to your edit definition, to your equation goal, select the value to change it to 3, check. Alright, once you change the value, we'll run the solver, save it, and run. So we already finished the solver for the Reynolds number of 10,000. We close this one. Okay, so we go to the results. This one, actually you could recycle the or use your CutTouch based on simulations. This one. Set to flux maximum. Check. Okay, since the value already changed, enter your project. Show. Okay. Then we go to the goal plot. Edit definition. Show. Also your DG force 0.002 at 0.19 drag coefficient. Let's go to the chart. Alright. At Reynolds number of 10,000, what is the value that we are able to get? Here. Got this one. So expect about Reynolds number is here 0.00. The value is to be at those values. Alright, so that's the end of our simulation.